All right, welcome back. We are going through the Level 3 paper from 2018, the differentiation paper for the calculus course. So we're on to question 2, and we've got this one here where we need to differentiate this expression. Now remember, 3 root x is just 3x to the power of a half. So dy by dx will be, to differentiate that part first, so we've got a half times 3, which is 3 over 2, x to the minus a half, reducing that power by 1. Now cosec, when we differentiate that, you can look that up on your formula sheet, goes to cosec cot. So we get negative cosec cot. So it's negative 5 cosec 5x cot x. And that's it. Okay, so for part B, we have a particle is traveling in a straight line. In fact, just pause and read the question yourself. So we've got ourselves a kinematics question where we're told the distance being travelled, that's s of t, and we want to work out the velocity. So to do that, to get to velocity from distance, we need to differentiate. And if we're differentiating the natural log, we first of all differentiate that term inside and divide it through by the original term. So that's using the chain rule on differentiating a natural log. And then we need to work out that velocity when t is 2, so after 2 seconds. So we substitute in t is 2 as follows. We get 15 over 9, which is 0.789, and then the final thing is to put the units on it. So our distance was measured in meters and the time is in seconds. So the speed will be in meters per second. Okay, now we're on to part C. Now these questions are actually some of my favorite ones because I think they're actually quite nice, easy merit questions. If you can wrap your head around what's being shown on the graph, these are pretty straightforward. Okay, so we've got some questions about this graph. So for the function above, what is the value of f of 1? So just go to when x is 1, what's the value on our graph here? Now the empty circle shows that it's not happening there. The full circle is it is happening there. So f of 1 will be 5. Okay, for part 2, for what values of x does the function not have a limit? Now, not having a limit means that we don't have the same number coming from the left and the right, and it also has to be finite to be a limit. So the places where that's not happening is here at -3. We're coming towards a different number from the left as we are from the right. So when x equals 3, that is not going to work. Oh, -3, sorry. And then the other one where that happens is at x equals 1. We get a different number if we're coming from the left and the right towards those points on the graph. So we have no limit at 1 either. The rest are all fine. There's nowhere else where we've got those different things happening from the left and the right. Okay, so find all of the values of x that meet the following conditions. Let's first of all start off with f dash of x is greater than 0. F dash of x gives us the gradient, so we're looking for anywhere where the gradient is positive. So that's going to happen on our graph. Here we've got this section here, up until the top of that maximum, where we have a positive gradient, and this section here. So that happens from 1 to 3 and 7 onwards. So here we can put when x is between 1 and 3 and x is bigger than 7. Now note that those are strictly greater than symbols, not equal to, because at x equals 1 we've got different things happening there, and the same at 3, it's the top of a maximum, so the gradient there would actually be 0, not greater than 0, and at our x equals 7 point, we've got two different functions joining, so we can't find the derivative at that point, so it has to be strictly greater than 7, not or equal to. Okay, part 2 is f dash of x equals 0 and f double dash of x is less than 0. So what this means is the gradient is equal to 0, and the gradient itself is less than 0, so negative, so the gradient is reducing. Or another way to think about it is that the gradient is a max, or the graph itself at that point has a maximum. Right, so gradient equal to 0, looking for a maximum point, so we have this bit just here. We got a maximum there, the gradient is 0. The gradient function is reducing as we move along, it's going from positive into negative, so that's going to satisfy our conditions of that, and that happens at x equals 3. Now the final part is f of x is continuous but not differentiable. So if we look back at our graph, we've got our points where we can't differentiate where there's breaks in the graph. Of course, that's discontinuous, but we're looking for where it's continuous, but we can't differentiate it. So we've got two other points of interest. We've got this one here at x equals 5. However, that's not continuous because we've got a hole there. So we've got this one that's left where it's continuous. We don't have any break in the graph, but we can't differentiate it because we've got that kink in it, that sharp corner. So at x equals 7, it's continuous but not differentiable. And part D is asking us to differentiate this expression, which is going to take a bit of product rule. So we differentiate each of those parts as u and v, and then put them together to work out the derivative of y using the product rule. So we're going to cross multiply across these two things, like so. And then we need to find the values of x for which dy by dx equals 0. So set this equal to 0, and let's go do some solving. So if we take out a factor of e to the x, then we can do this to try and simplify things. Once we get to here, either e to the x equals 0 or the bracket is equal to 0. Now e to the x can't be 0, so we say that's not valid. That's not going to give us an answer. We'll carry on with this one and factorize out to get our, and we get down to x being a half or minus 2. Alright, part E. We've got a bit of a tricky rates of change question with this one. So just take a pause to read and take in what we're being told. So to start off with, see if you can label some rates in the question. So we've got the rate that the water's coming in. So that's the volume and how it changes according to time. So dV by dt will be 150. We've got a cone. We're going to need to know the volume of that cone. So volume is 1/3 pi r squared h for a cone. We also have a link between r and h with the similar triangles that go on, where we've got this 200 to 80 relationship. So h will be equal to the radius multiplied by 5/2, which means we can put that into our volume equation and eliminate h, and then we get that our volume will be 5/6 pi r cubed. Okay, now the other rate involved in this question is here, so it's the rate of the surface area. So the rate that the area changes according to time, that's what we're looking for. So we're going to need to use some chain rule on this. Now what we want to work out is dA by dt, so let's start there. Now what we know is dV by dt. So what would we need to times that by to get dA by dt? We would need to multiply it by dA by dV, so that the v's cancel and we're left with dA by dt. So this brings up a little bit of a snag, because we've got dV by dt, but we don't have dA by dV, and we don't have a formula linking them, so we've got to make another one. So to work out dA by dV, we would need to do something, some sort of chain rule to work that out. So what could we do with the area? Well, the area we're talking about is this surface area here on the top of the circle there. So that will be pi r squared, which gives us a formula that links A and R. So from that we can work out dA by dr, which would be 2 pi r. So back to our wanting to know dA by dV. Now we've got dA by dr, what would we need to times that by to get dA by dV? We would need dr by dV, so our dR's cancel out. Now we have a formula linking v and r right here. So we can go and do dv by dr, differentiating v with respect to r. So we get 5 pi r squared over 2. Okay, so if we pop that back into our chain rule to work out dA by dV, then we get dA by dr is 2 pi r, and dr by dV is the reciprocal of this dV by dr that we just worked out. So that'll be 2 over 5 pi r squared. So those pi's cancel out, one of the r's cancel out, and we're left with 4 over 5r for dA by dV. Okay, now we can go back to working out dA by dt. So we can substitute in dV by dt, that was this 150 up here, and dA by dV that we just worked out over here is 4 over 5r, which equals 120 over r when you put them together. So when h is 125, because this was what we were trying to work out from the beginning, what's that rate when the depth of the water is 125? So when the height of that water is 125, r will equal 50. Now where do I get that 50 from? That was back up here, remember when we were working out a link between h and r, so h is r times 5 over 2. So for h to be 125, r must be 50, and that gives our rate as 2.4 if you substitute into 120 divided by 50. So then put our units on it. We are measuring the area, which was in, what was that measured in? Centimeters. So we are measuring in centimeters squared, and the time we were measuring it was in seconds. So centimeters squared per second. And you made it through the excellence question. That was quite a tricky one because there was quite a lot going on and you had to figure out what linked to what, but just take it one step at a time. If you get stuck on those ones, just start writing down formulas that link different variables, differentiate them, see how you can put them together in a chain rule. Alright, so next up on the playlist will be the answers to question 3 from this paper. If this video was helpful to you, like it, subscribe it, help others to find it. Thanks!